Yeah, so today I'll be covering shear force and bending moment diagrams, both drawing shear force and bending moment diagrams from the loading diagram and drawing the loading diagram from the shear force diagram. Okay, so this is very important concept of structural analysis. So I'll be discussing question number 32 of GATE 2009. So this question, we are given two groups. In group one, there are shear force diagrams, and in group two there are loading diagrams. So we have to match that which shear force diagram belongs to which loading diagram. Okay, so this is a reverse problem. So before discussing this problem, I'll discuss how to make the shear force and bending moment diagram quickly, and after discussing all those concepts, I hope you'll be able to solve this question yourself. Okay, then at last I'll discuss this problem. So let us discuss how to quickly make the shear force and bending moment diagram. Because in GATE we do not have that much time to calculate each and everything. So we'll see how can we quickly solve this problem in half a minute. Okay, we'll not if we will know the concept, we'll learn the concept I'm telling you right now, then you'll be able to solve this problem within a minute. Okay, so let's discuss. Yeah, so as I have said earlier, so I'll be discussing the concepts first. So this is the sign convention I'm going to follow. That is, if the bending moment causes any section to have a curvature like this, to sag, to have a curvature like this, then I'll consider that moment as positive. If any moment causes any section of the beam to hog or have a shape like this, then I'll call it as negative bending moment. Okay, similarly for shear force, whenever the sum of all the transverse forces on the right side of the section is in downward direction, I'll call it as positive. And whenever the sum of all the transverse forces, that is the shear force, at right side of the section is upwards, I'll call it as negative shear force. So this is the sign convention I'm going to follow. Okay, so I hope it is clear. Sagging bending moment positive, hogging bending moment negative. If the shear is something kind of this shape, it is positive, and otherwise it is negative. Okay, so this thing will be more clear when I'll solve the problem. Okay, so please watch it carefully. So I'll be discussing few points. With the help of these points, you will be able to quickly draw the shear force and bending moment diagram from the loading diagram, as well as the loading diagram from the bending moment and shear force diagrams. So let's start. So please note down these points. These are very important. Slope of the shear force diagram is equal to the intensity of the distributed load. Okay, just remember these points for now. Then when we solve this problem, then I'll tell you how to implement this thing. Just for now, just remember these points which I'm telling you. The slope of the shear force diagram is equal to the intensity of the distributed load. Okay. The second point is, for example, just I'll explain it quickly. Suppose this is a shear force diagram, a random shear force diagram. This slope of shear force diagram here is positive or negative? It is a positive slope, right? This is called a positive slope and this is called a negative slope. So at this section, the slope is positive. It means that it will have, the intensity of loading is positive. Positive intensity of loading means upward load. So it will be having upward load in this section. Okay, so positive slope if the shear force of the slope of the shear force diagram is equal to the intensity of the distributed load. So please remember this formula. I'll tell you how to implement this while we solve the problem. So dv by dx, that is the slope of the shear force diagram, equal to the intensity of the distributed loading. The second point is the slope of the bending moment diagram is equal to the shear force at that section. I hope these things are already known to you, but just remember it and we'll see how we can implement this in the problem. So the slope of the bending moment diagram equal to the shear force at that section. Okay. Third point is change in the shear force equal to the area of the distributed loading between those two sections. It means that we can also write it as delta V equal to area under the distributed loading, that is integral over wx dx. Don't worry, we do not have to solve any integral here. It's just a symbolic thing. So delta V, we can also write it as V2 minus V1. Delta V is change in the shear force, that is V2 minus V1 equal to Wx dx, that is the area under the distributed loading. Okay. So these are just symbolic things. We do not have to solve any integral here. Just remember that. First, the thing you have to remember is dV by dx equal to Wx. That is the slope of shear force diagram equal to the intensity of the distributed loading. The second thing you need to keep in mind is dm by dx equal to V. That is slope of the bending moment. Dm by dx, when we calculate the slope, we do the differentiation, right? So dm by dx equal to shear force at that section. The third point is the change in the shear force equal to the area under the distributed loading. So we can write it as delta V equal to integral over Wx dx. Fourth point is the change in the bending moment diagram equal to area under the shear force diagram, that is delta M equal to integral over V dx. We can also write it as M2 minus M1 equal to integral over V dx. So these are the 4 points you need to remember, the 4 formulas which we will be implementing while drawing the SFD and BMD for our problem. Some other points you should note down is con- consider the effects of point load. So we will consider the effect of point load and concentrated moments separately. Whenever we have downward point load, then shear force drops by F amount at that section. Okay. Whenever we have downward point load, the shear force will drop by F amount. Whenever we have upward point load, shear force jumps by F amount. Okay, please note these points. Whenever we have an upward point load suddenly, suppose this is a part of a beam and we have a upward point load F. So if the shear force diagram was going like this, it will jump suddenly like this. So it will have a sudden jump at this point. Okay. The other point is clockwise moment. Clockwise, if there's a clockwise moment M, then the bending moment jumps by M amount. So clockwise moment M will jump the bending moment diagram by M amount. Anti-clockwise moment M will drop the bending moment diagram by M amount. So these are the, I think total 8 points are there. You should remember these 8 points, and using these 8 points we will solve our problem. Any problem till now? I know it sounds vague at this point, but we will see how to do it. Okay, then this thing I'll directly come to the problem, but before that there are some other important points also. Zero slope, this is how we denote a zero slope, right? This is a zero slope. What is a constant positive slope? This is a constant positive slope. I hope it is clear, right? You know a slope. This is constant positive slope. Constant negative slope is something like this. This is constant, and in negative direction it is decreasing. So constant negative slope. This is positive decreasing slope. So how it is positive decreasing slope? At this point, the slope is this. Say it's theta. At this point, the slope is, so this slope is constantly decreasing, right? Here it is more. If we draw the tangent here, the slope is theta here. If we draw tangent at this point, it will have theta 2. So theta 2 is less than theta 1. So it's a positive decreasing slope. It is in positive direction. It is in positive direction, but it is constantly decreasing. So it's a positive decreasing slope. Just remember this for now. It's a positive decreasing slope. This is a negative increasing slope. How is it negative increasing slope? It is negative, you know, right? It is going downward, so it is negative. Why it is increasing? So when we draw a tangent at this point, it's a zero slope, right? When we draw tangent at this point, it is theta. When we draw tangent at this point, it is even bigger theta. So it is negative, but it is increasing. I hope this is clear. Okay. If there's problem with this, please let me know. Okay. Positive. Just note down the shape. Constant negative slope. Positive decreasing slope look like this. Negative increasing slope looks like this. Negative decreasing slope. It is also negative because it is going downwards. How it is decreasing? Just draw the tangent. Here the tangent, it is theta here, that much big. Draw tangent here, it is reducing. So it is negative decreasing slope. So for you, you just need to remember the shapes. The first shape is zero slope. This is zero slope, no slope at all. This is constant positive slope. This is constant positive slope. It is constant. It is neither increasing nor decreasing, but it is in positive direction. Okay, so it is positive, but it is constant, right? Everywhere, if we draw the tangent, it is theta everywhere, right? So it is constant, but it is in positive direction. So it is constant positive slope. This is also constant everywhere. If I'll draw the tangent, it will be theta everywhere, but it is constant negative slope because it is going downwards. Then positive decreasing slope, as I've told you already, this is positive, going in positive direction, but it is constantly decreasing. This is negative increasing slope, this is negative increasing slope. Okay, and similarly it is negative decreasing slope. Please note down the shapes. Okay, this shape will help us in drawing the SFD and BMD. Okay, so please note down the shapes. What is zero slope, what is constant positive slope, what is constant negative slope, and similarly everything. Okay, now I'll directly jump into the problem so that we could implement the concepts which we have studied. Okay, so this is our first problem. I hope you know this drawing SFD and BMD of this, but we will use our method, what we have discussed so far. So this is point load P at the mid depth, right? So what will be the reaction here? The reaction will be P by 2, and here it will be P by 2. I hope you know how to calculate the reactions, right? So since this load is P is at the mid depth, so the reactions will be P by 2 and P by 2. Okay. Now let us quickly draw the SFD using the concept we have discussed. So I am drawing the sign convention here. So this is the sign convention we will follow in every problem. That is sagging bending moment and this type of shear force as positive. Okay. Now let us draw the SFD of this problem first. So to draw the SFD, we'll start with this point. Okay, let us call it as point number A, let us call it as point number B, and it as C. Total length is L, so this will be L by 2. This is L by 2, and this will also be L by 2. So the reaction will be, since it is at the middle, so the reaction will be P by 2 and P by 2. Okay, so for now I'll just remove it so that I could draw the SFD. Now this is the sign convention we are following. So if there is a section and in the left side, if the load is upward, the shear force is upward, then we will consider it as positive. So this section, this load is upward, so we will draw it like this in upward direction. It is P by 2. Okay, it is P by 2. Why we have drawn it upward? Because we are following this sign convention. So according to this sign convention, if the shear force on the left side is upward, so on the left side it is upward, so we have drawn it as positive, so it is P by 2. Now in the section from section A to C, there is no load, right? There is no load, neither point load, neither um W, or the uniformly distributed load. So we will draw it as constant. Okay, I hope it is clear. So it will remain constant till point number C. Now what will happen at C? So what was our point there? Yeah, so the point was downward F point load. Due to this downward F point load, shear force drops by F amount at that section. So this point we are taking, downward F point load causes shear force to drop by F amount. So in our problem, we have encountered a point load P, which is in downward direction. So our shear force diagram will drop by P amount. So here it was P by 2, right? Here it was P by 2 constant, but now it will drop by P amount. So P by 2 minus P is P by 2 minus P is minus P by 2, right? So it will be minus P by 2 here, minus P by 2. So we will join this. The next thing is no load in section C to B, there is no load. So it will remain constant up till this. Here it will be minus P by 2. Now what is happening? We have an upward point load. We can also consider it as an upward point load. Here it is upward point load. So upward point load will jump the shear force diagram by that amount. So is an upward point load of P by 2 amount. So our SFD will be jump by P by 2 and it will become 0 here. So it is our complete SFD. Here it is positive, here it is negative. It was a very simple question. If you will do it with your usual technique, I hope you'll get the same answer quickly. Any problem till now? I hope it was very easy. So I'll move towards the bending moment diagram now. Okay, so bending moment diagram, we'll use our formulas which I have discussed. So I've used the formula m2 minus m1 equal to integral over v dx. This formula I have told you for drawing the bending moment diagram. See how will we use this formula. So in this beam, we know that at section A the bending moment is 0. Why at section A bending moment is 0? Because section A is a hinge. Similarly, at section B also the bending moment is 0. Okay, now we don't know the bending moment at section C. Okay, other than that, at section A we know, at section B we know, but we don't know the bending moment at section C. Now we will first draw the bending moment for section AC. So I'm drawing it for section number AC. So how will we use this formula? Consider this as section 2 and this as section 1. So I am using the formula m2 minus m1 is equal to integral over v dx. M2, that is at this section. We don't know the bending moment at this section right now. So this is M2. We know the bending moment at section 1, which is 0, right? At section 1, the bending moment is 0. So M2 minus M1 equal to integral over VDX. What do we mean by integral over VDX? Integral over VDX means the area of shear force diagram for that section. So area of shear force diagram for section AC is, what will be the area? What will be this area? This is a simple rectangle, right? So area is P by 2 into L by 2. This is the area of this rectangle. So M2 will come out to be PL by 4, right? So M2 we know now, plus PL by 4 or minus PL by 4. It is plus PL by 4, right? So it is PL by 4 here. Now we know all the three bending moment, all the three, we know bending moment at all the three sections now, right? At section A also we know the value of bending moment, which is 0. At section B also we know, which is 0. At section C also we have calculated the bending moment as PL by 4. Now what is the shape of this bending moment diagram? I can join it using this shape also, I can join it using this shape also. So what will be the shape? Okay, the shape we don't know. So to determine the shape of this bending moment diagram, we know that shear force, I am rubbing this, I hope I can rub this now. We noted it down. So V, another formula we have discussed is shear force equal to dm by dx. That is, shear force at that section, at a section, is equal to the slope of the bending moment diagram. So we will analyze this, the shear force at section AC now, because the trend of this shear force will be equal to the slope of the bending moment diagram. Let's see. At section AC, shear force is, tell me whether you agree with me or not. Okay, at section AC, shear force is positive and constant. Do you agree or not? At section, for section AC, the shear force is positive and constant. It is neither increasing nor decreasing, right? Do you agree with me or not? You can write maybe yes or no in the comments, because this is very important for it. Do you agree? At section AC, the shear force is positive and constant. So the slope of the bending moment diagram will be positive and constant, because we are following this formula. According to this formula, V equal to dm by dx. Since V, that is a shear force, is positive and constant for section AC, therefore the slope of the bending moment diagram will be positive and constant. And I have discussed this formula. What is positive and constant here? This is the constant positive slope, which is a straight line as, right? This is a constant positive slope. So we'll make this the same shape here, that is positive and constant, right? Now we know the shape of bending moment diagram for section AC. Okay. Now we will see section number CB. For section CB, the shear force diagram is negative and constant, right? For section CB, the shear force diagram is negative and constant. So the slope of our bending moment diagram will be negative and constant. What is negative and constant here? This is negative constant slope. That is this kind of slope. So we will draw this shape here, and our bending moment diagram is done. So this is the bending moment diagram, and value we have already calculated at this point, PL by 4, right? So this is the complete SFD and BMD using the concept I have discussed. Okay, so this was a very easy problem. You can do it regularly, like in your regular way also, but using this, the method I have discussed, I have told you. Now we will see another problem using the same method, okay, so that it will be more clear. Now we have another thing, another problem, in which it is W kilonewton per meter, suppose, and this is length is L meter. Let's see. So we need to draw the SFD and BMD for this beam. So first of all, what we will do, we will calculate the reactions. So can you tell me the reactions? It is very easy. What will be the reaction at A and B? Can you quickly tell me in the comments? Please try to do it with me so that everything will be more clear then. What will be the reaction at A and B for this kind of loading? It is very easy, right? Total load is WL, right? Total load is WL, right? Because this is W kilonewton per meter. So the reaction at Nikesh is right. The reaction at A will be WL by 2. Half of reaction will be distributed, so it will be WL by 2. I hope you know these small things. Okay, so I'm considering you know this thing. Then how to draw the SFD and BMD using the concept we have discussed. So for drawing the SFD, I'm following the usual sign convention, and this is the sign convention. So I'm starting with this point here. Okay, so this is the left point. So if the left, at the left section, the load is upward, so we'll draw, it will be a positive shear force. So we have drawn it as a positive shear force. Now we can directly do at this point also. At this point, this is the right side of the section, this is the right side of the section, and the load is upward. So at right side, downward load is positive but upward load is negative. So I've drawn it at this way, WL by 2. Okay, now how to join these two points? So the point at every section we know the value of shear force, but how to join this thing, whether I should join it like this, whether I would join it like this, we don't know, right, at this point. So how to join it? So we know this formula: loading equal to the slope of shear force diagram. So we will see what is the type of loading. So loading is downward. Downward loading is negative. So loading is negative and constant. The loading is not increasing nor decreasing. W is constant everywhere throughout the beam and it is negative. So the slope of shear force diagram will be negative and constant. What is the shape of negative and constant? Negative and constant is like this. So we will join it with this thing. Sorry, it is not very straight. Yeah, so it will be the shear force diagram for this. This part will be positive and this part will be negative. I hope it is clear. So these are very easy problem which I'm discussing right now. So I'll make it more and more difficult in the next few problems. Okay. So now we have drawn the shear force diagram for this beam. Now I'll move towards the bending moment diagram. Okay. So how to draw the bending moment diagram? Since it is a simply supported beam, so first I know here the bending moment is 0. At B the bending moment is 0. Right? Let us calculate the bending moment at C. Let us call this at C. Okay, let us calculate the bending moment at C. So we will use the formula m2 minus m1 equal to integral over v dx. The same formula for calculating the bending moment at another section. We will use this formula m2 minus m1 equal to v dx. Let us call it as section 1. Let us call it as section 2. M2 at section 2, the bending moment we do not know. At section 1, do we know the bending moment? At section 1, the bending moment is 0, equal to integral over VDX. Integral over VDX means the area of shear force diagram for section AC. So for section AC, what is the area of this shear force diagram? It is a triangle, so it is half base into height. Height is WL by 2. Right, so m2 we comes out to be WL square by 8. So at section 2 now we know the value of a bending moment, which is WL square by 2 by 8. Okay, so now how to join? What should be the shape? Okay, should we join it like this? Like in the earlier problem we have joined it like a straight line. So what should be the shape now? For drawing the shape, I'm again considering the same thing. Yeah, I'm again considering the same formula. So V equal to dm by dx. Okay, so we will see what is the area of shear force, how the shear force is varying, and that will be the same, that will be same as the slope of the bending moment diagram. Okay, so this is slope. Okay, slope of bending moment diagram. So we will see in section AC how the shear force is varying. So in section AC, okay, please listen to me carefully. In section AC, the shear force is positive and decreasing. Do you agree? The shear force for section AC is positive. It is positive, right? Because it is above the axis, it is positive and decreasing. Do you agree or not? Please write in the comment section. For section AC, this shear force is positive and decreasing. So what is the shape of positive and decreasing slope? I have discussed this already. The positive decreasing slope looks like this. This is positive, but it is decreasing. Why positive and decreasing? I'll tell you again. Because here, if you draw a tangent, it is theta. It is theta 1. Okay. And here, if we draw the tangent, it is right again. So here, if you draw the tangent, it is theta 2. So theta 2 is less than theta 1. So it means the slope is constantly decreasing, but it is positive. Okay. So positive decreasing slope. So it will be positive decreasing slope, and it will be like this, positive decreasing slope. Now for section CB, the shear force for section CB, this is section CB. For section CB, the shear force is negative and increasing. Do you agree? The shear force at section CB is negative but increasing. It is negative but it is increasing, right? When we move towards the right side, it is increasing. For section CB, the shear force is negative and increasing. So the slope of the bending moment diagram will be negative and increasing. What is negative and increasing slope? This is negative and increasing slope. Like this. This is negative. It is going downward, so it is negative, but it is increasing because here the slope is 0, here the slope is theta. It is increase. Okay, so since the shear force diagram is negative and increasing, therefore the slope of the bending moment diagram will be negative and increasing. So how, what is the shape of the negative and increasing? What is the shape? This is negative and increasing. So this will be our bending moment diagram for this problem. Okay, I hope this thing is clear to you. Just remember these 4 5 formulas. This formula you need to remember. You need to remember m2 minus m1 equal to shear force diagram area, and you need to remember w equal to dv by dx. So these 4 5 formulas you need to remember. And in the in during the gate exam, you need not solve the um, uh, entire thing. You can just see the shape from the options and take your answer. Okay, if you are satisfied with the shape, then you can take your answer then and there only. You need not to calculate every reaction and everything. So this is the benefit of this technique, that you need not to solve the entire problem. You can just see the shape from the given options and you can tick mark your answer. Okay, I hope it is clear. Now we will move towards a slightly more uh, complicated problem, you can say. So in this problem, first we need to determine the reactions. So I'm telling you how to draw SFD and BMD from loading. Then I'll move towards drawing loading diagram from the SFD diagram. Okay. So in this problem, first we need to calculate the reactions. So either you can calculate the reactions in a conventional way, as you would be doing in your classroom, but I'll tell you one method to calculate the reaction. If it suits you, you can opt that. So I'll tell you how to calculate the reaction. So in this problem, how to calculate the reaction due to a point load. So this point load 600 kilonewton is at the center of the beam. Okay, so the reaction due to this 600 kilonewton will be, so I'm calculating the reaction separately for the 600 kilonewton load, and then I'll calculate it for this 4000 kilonewton meter moment. Okay, so this is 600 kilonewton. Since it is at the center of the beam, this will be 300 and this will be 300. Then due to this moment, which is 4000 kilonewton meter, then I'll calculate the reaction due to this 4000 kilonewton meter moment. So what is the, how to calculate the reaction due to this moment quickly? So the reaction due to this moment will be moment divided by the length of the beam. Moment divided by the length of the beam for both section A and for section B. For example, it will be 4000 divided by, what is the length of the beam? 20. Here also it will be 4000 divided by the length of the beam. And what will be the reaction? What will be the direction? The direction will be, if this is in clockwise direction, so the reaction will develop such that it will form anti-clockwise couple. So the applied loading is clockwise, so the reaction will develop such that it will form an anti-clockwise couple. So how to draw that? Let me draw it first and then you'll tell me if I'm correct or not. Okay, for drawing anti-clockwise couple, this should be the direction of the reaction. This reaction at A and reaction at B, is it forming an anti-clockwise couple or a clockwise couple? Is it trying to rotate this beam in clockwise direction or anti-clockwise direction? Forget about this moment for now. This reaction which I have drawn at A and B, are they trying to rotate this beam in clockwise direction or anti-clockwise direction? Can you please write that in comments? Anti-clockwise direction. That is great. I hope everybody is getting that right. It is so the reaction will develop such that it will be opposite to the applied moment. Okay, so this will be the direction of the reaction. Now we can simply add these two things and our final reaction will be 300 minus 4,000, because it is downward direction, right? Minus 4,000 by 20. The reaction at point B will be 300 plus. Why plus? Because it is also upward and it is also upward. 3,000 plus, sorry, 300 plus 4,000 divided by 20. So final reaction at here will be 100, because it is 200. Right? Reaction will be 100. The reaction, final reaction at here will be 500. Okay, so this, in this method you can quickly calculate the reaction. Otherwise you can calculate the reaction in your conventional way also. Okay, the calculating reaction is not my issue here. I am just telling you how to draw the SFD and BMD. So this is a quick method to find the reaction. Okay, it does not depend on the amount of reaction does not depend on the location of this moment here. Please note that. Okay, for section if it would have been here also, then the thing would be same. Okay, so this is the method of calculating the reaction. So we have calculated the reaction. The reaction at A is 100 kilonewton and the reaction at B is 500 kilonewton. Okay, now we will see how to draw the SFD and BMD here. Okay, now we'll start with drawing the SFD for this question. I'm following the same sign convention. This is positive shear force. Okay, now we'll start with this section. So at section A, there is a reaction 100 kilonewton, which is upward direction. So when the left part of the section is upward, the shear will be positive. So here we will draw 100 kilonewton in upward direction. So we know the shear force at section A. Now we will, let's call it as section C and this as section D. So from between section A and C there is no point load, right? So it will go straight like this. Okay, and the value here will also be 100 kilonewton, right? Now at point C there is a point load of 600 kilonewton. So due to this 600 kilonewton, as I've discussed earlier, due to this point load there will be a sudden drop in the shear force diagram. So by how much amount? By the amount of that particular loading. So in this case the shear force diagram will drop by 600 kilonewton. So earlier the amount was 100 kilonewton. Now it will drop by 600 kilonewton and our final answer will be minus 500 kilonewton. So at this section it will drop by 600 kilonewton and it will be minus 500. So it is not to scale. It is minus 500 kilonewton. I hope it is okay. Then between section C to B, there is no loading. Okay, no, neither it is a point load nor it is a uniformly distributed load. Please note another point, that the moment or the couple will not affect the shear force diagram. Okay, it will not affect the shear force diagram. It will only affect the bending moment diagram. So even if there is a couple somewhere or the moment applied moment somewhere, it will not affect the shear force diagram. Therefore, we will neglect it for for drawing shear force diagram. We will neglect moment for drawing shear force diagram. Please note this point. So from point C to B, there is no loading, right? Neither point load nor uniformly distributed load. So it will go straight up till here. Hmm? will be straight line up till this point. Now at B, there is an upward point load or upward reaction of 500 kilonewton. So upward reaction is positive. So earlier it was minus 500 kilonewton here, right? It was minus 500 kilonewton. Due to this point load, it will go upward and it will become 0 here. So this is the SFD. This is positive part and this is negative part. Is there any problem with SFD here? The important thing to note here is that the couple or the moment which we have applied here will not affect the shear force diagram. It will only affect the bending moment diagram. Okay, so if shear force diagram is done, I'll move towards the bending moment diagram. Okay, so to draw the bending moment diagram, we will use this formula m2 minus m1 equal to integral over v dx for every section. Okay, so this is section, this is A point. So at point A and at point B, bending moment will be 0 because at A it is hinge and at B it is also hinge, so it will be 0 0 here. Now let us call it as section 1 and it as section number 2. Okay, so we do not know the moment at section number 2, so m2 we do not know. Do we know m1? M1 we know, which is 0, and integral of vdx means the area of shear force diagram between section A and C. So the area of shear force diagram between section A and C, right? So what is the area? It is a rectangle between A and C. So area will be 100 multiplied by 10. So M2 will be 1000 kilonewton meter, right? M2 we have calculated as 1000 kilonewton meter. Now we know M2 also. 1000 kilonewton meter. I'm not drawing the shape for now. Let's see what would be the shape. So to see the shape, we will see this v equal to dm by dx. So what is the trend of shear force for section AC? For section AC, the shear force is positive. For section AC, the shear force is positive and constant. Therefore, slope of the bending moment diagram will be positive and constant. Positive and constant means this kind of slope, right? Positive and constant means this slope. Okay. Now, we know up till M2 we know. Now, just remove it. Let us call this as section 1 now and this is section 2 now. Okay. Now again we will use the same formula, m2 minus m1 equal to integral over v dx. M2 we do not know, m1 we know, m1 is 1000. This is m1, right? M1 is 1000 now. Integral over v dx, that is area of shear force diagram between section CD, this area. So this area is minus 500 multiplied by this length is 5. So it is 5 here. So m2 will be minus 2500 plus 1000. So m2 will be minus 1500 kilonewton meter, the unit. So it is minus 1500 kilonewton meter. So we know now that at section 2, that is at section D, we know the value of bending moment, that is minus 1500. So I'll mark it here, minus 1500. What will be the shape now? Shape will be at section between section CD, this area, the shear force is negative and constant. It is neither increasing nor decreasing, but it is negative, right? So negative and constant is this kind of shape, right? So we will join it with this straight line here, right? I hope you agree. Then for just I'll remove this thing because it is make it a little shorter. That is 500, right? Now we will move towards section DB. For section DB, let us calculate the value of bending moment at section D. But before that, at section D, we have a couple which has a value of 4000 kilonewton meter, and the direction of this couple is clockwise. So I have discussed this point earlier. Whenever there is a clockwise couple, then the bending moment will jump by that amount. If there's an anti-clockwise couple, the bending moment will drop by that much amount. So here we have a clockwise couple, so our bending moment will jump at point D by 4000 kilonewton meter. So earlier it was minus 1500 kilonewton meter. Now it will jump by 4000 kilonewton meter, and it will become 2500 kilonewton meter. So at section D, now it will jump up till this point and it will become minus 2500 kilonewton meter. These are important points. That is why I've discussed it earlier. You should remember these formulas like this one. You should remember what is positive slope, what is negative slope, what is positive increasing slope, what is positive decreasing slope. These slope types you should remember. The another thing, point you should remember is these small points, like whenever there is a point load which is in downward direction, then the shear force diagram will drop by that much amount. Whenever there is a clockwise couple, the bending moment diagram will jump by that much amount. So these points you should remember. Now, at only point is remaining is point number B. So at point B we know that bending moment is 0 already. So how to join this DB? So will see the shear force at this section. So the shear force in this section is negative and constant. So the slope of the bending moment diagram will be negative and constant. And what is the shape of negative and constant? It is like this. So this is the shear force diagram. So it seems like a y negative, y, ma'am, y negative 25. Oh, sorry, I'm sorry. I've just written it negative. It is positive, right? I've drawn it positive, but by mistake, I've written it negative. Okay. Is it clear now? So I hope it is clear now. So this is positive. This is negative. It is positive. So it seems like a complicated problem, but if you know these things, it will be within a 2-3 minutes you'll be able to draw this SFD and BMD. Okay, just you should remember these small formulas. So I hope I wanted to discuss some more questions, but I think time is less, so I'll jump directly to our problem, that the gate problem which we intended to discuss. Okay, so I hope with this knowledge you'll be able to guess the correct answer. Okay, so let us discuss. So in this problem, we for in gate we just have 1 or 2 minutes to solve a problem. So considering that fact, but here we have four things. Okay, so how to approach this problem? So in this problem, the options which are given to us is a for all the options, either the p matches with 3 or p matches with 2. Okay, so we will consider these two things only. Either I'll check P with either 2 or 3. Okay, because according to the options, there's no like P4 or something like that. Okay, so yeah, so let's see how to match this P thing. So for the problem P, we have this kind of, just a minute, I'm sorry. Yeah, so for problem, oh, God. This is the, yeah, I'm sorry for this. Yeah, so let's see what how to match P. So as I've told you earlier, the P matches either with 3 or with 2. Okay, so we will see P now. So when we see section number, let us call it section A, this has B, this has C, this has D, and this has E. Okay, when we will see section AB, then the slope of shear force diagram is negative and increasing, right? Okay, so either the option is 3 or 2. So I'll check 3 or 2. So yeah, so do you want to guess what should be the answer here? It should be 2 or 3. Okay, let me tell you then. At section AB, the slope of shear force diagram is negative and increasing. So when we see third one, the intensity of loading for section AB is negative and constant. But when we see second one, that is 2, there is only point load. That is, there is no like negative and constant thing is not there. But here we have loading negative and constant. So we know this formula, right? Loading intensity is equals to dV by dx. So how the load is varying is related to the slope of the shear force diagram. So when we see second there is a point load. If so if there is a point load, the shear force diagram for this thing should be something like this. It should be constant. But here the shear force diagram is negative and it is increasing. So negative and it is constant. So negative and constant matches with this, right? Is there any problem with this? Okay, I'll explain it again then. Sorry, there was a disturbance. Yeah, so W equal to dV by dx. So if we want to know the slope of shear force diagram, we should see how the load intensity is varying. So from the options, we can only match P with either 2 or with 3. So when we see 2, so for 2, if the shear force diagram should be something like this. It should be constant. So we have seen it here also. Whenever there is a point load, so shear force diagram is like constant. Okay, but in our problem, the shear force diagram is negative and constant. So negative and constant means the loading should be negative and constant. So negative and constant loading for section AB is for third option only. Okay, for third option only. And for first option also, we have negative and constant loading. But in our option, P does not matches with 1. Okay, if it would, if in some option, it is like P1, then we have to analyze first option also. But we are not analyzing first option because in our option, P only matches either with 2 or with 3. Okay, I hope it is clear. So either the answer is, so P matches with 3. So either A is right or B is right. Okay, P equal to 2 is not right. So these two options I have removed already. Okay, I hope it is clear. Then we will see second thing. Then we will see Q. Okay, so let's see Q now. So in Q, let us call these sections as A, B, C, D. Now, Q either matches with 1 or 4. So we will analyze only option 1 and option number 4 for Q. Okay, let us see option number 1 first. So in option number 1, it is okay, right? So in option number 1, for Q, we know that for section AB, the shear force diagram is negative and constant. It is negative and constant. So the load intensity for section AB should be negative and constant. In which option the load intensity for AB is negative and constant? In option number 1 or option number 4? Please tell me in option number 1 or option number 4, in which of the following options the load intensity is negative and constant? Great. So in first option, load intensity is negative and constant. So A will be our answer. We do not need to solve other things, R or S. In just half a minute, we could guess that what would be the correct answer. Okay, so this type of this slope thing and everything will help us in solving this type of problems. Here we do not need to make the loading diagram for each and every SFD diagram or SFD diagram from the loading diagrams. You can just see the shape of the SFD diagram. Okay, this slope or something like that. I hope it is clear. It was an easy problem. Okay, but it seems like difficult. But with this procedure, we can easily solve this problem in a minute. Okay. So in this way, you should approach the gate problems. You should first see the options. You need not solve to match each and every pair with each other. You can just cut down your options a bit before solving the actual problem. Is it clear? So in next class, I'll discuss few more problems, because till now I've only discussed how to draw SFD and BMD from the loading diagram. In the next class, I'll show how to draw the loading diagram from the SFD diagram in a similar manner that I have discussed in this gate problem. So I'll discuss few more problems, how to draw the loading diagram from SFD and BMD diagram. I hope time is over. But quickly, do you want to tell me this answer? So this is a BMD diagram, right? It is a BMD diagram which is given to you. Okay, so in this BMD diagram, the question they are asking is, the beam is possibly under which of the following loads? Okay, so this beam is under which of the following loads? So options are couples of M at C and 2M at D, couples of 2M at C, M at D, concentrated loads of M by L at C and 2M by L at D, or concentrated load of M by L at C and couple of 2M at D. So do you want to guess? It's a very easy problem. You don't need to solve anything. Just by the concept I've discussed so far, what should be the correct answer? D. And please, others also answer. Try to answer. What should be the answer according to you? Then if you'll tell me the answers, then I'll discuss the solution. Nikesh is saying A. And what about others? I can't see this. Athisaya, huh? It is A. Okay, great, great. I know. No. Okay, okay. So you have understood the concept, right? So why A? Because option A says couples of M at C. So there's a couple M at C and 2M at D. So I've already discussed this, that the bending moment, the clockwise couple causes jump in the bending moment, and anti-clockwise couple causes drop in the bending moment. So in the loading diagram, there would have been a clockwise couple at C and D. So the magnitude of clockwise couple would be M, because here the bending moment jumps by M amount. Here the bending moment jumps by 2M amount, right? It jumps by 2M amount. So in the loading diagram, there would have been a couple of M at C and 2M at D. I hope it is clear. Okay, because here the bending moment diagram jumps by M amount. Here the bending moment amount jumps by 2M amount. So M and 2M accordingly. I hope it is clear, and it is time is over for today. So I'll discuss rest of the problems in the next session. So in the next session, I'll discuss how to draw loading diagram from SFD and BMD diagram and some other gate problems. Please try to practice this. I'll share the recording of this class so you can practice this thing at your home. Okay, then if there is no problem, I'd like to close the session for today. Is it okay? Should I close? If you have any doubts, you can ask. Okay, ठीक है. Thank you so much for listening. Okay, then bye. We'll meet in the next session.